To kick things off, I think we have three people here who are building foundational companies in ZK, but are all building things that are incredibly different. It would be great if we could go around, we could introduce ourselves, and we could talk a little bit about the things that we're working on.
Okay, hi everybody. I'm Jens. I'm the chief scientist at Nexus. And we are building a ZKVM. It's you can take a RISC-V program, and you can prove that it's executed correctly. We are been going through the Nova family of folding proofs, so Nova and Supernova and Hypernova. The ZKVM also has a Jolt implementation inside. And then we have a proven network that we just launched in October that can run in parallel the ZKVM. And we had 70,000 people supplying compute to it during that test from a couple of hundred countries. And we proved 700 millions of cycles of Fibonacci during that test.
That's incredible. It's an amazing scale.
Hi, I'm Francois. I'm the CTO at Argument. So at Argument, we do two things. One on the proving side, one on the verification side. On the proving side, we're doing another ZKVM. But where most ZKVMs are really focused on, let's say, the assembly of a particular CPU, let's say RISC-V, MIPS, that kind of thing, we're interested in proving directly using the evaluation semantics, the reduction semantics of a high-level language. So in our case, Lisp, very soon in a couple of weeks, or Camel, and then we will move on to greater and bigger things. And on the verification side, we're doing a verification layer that is actually a decentralized L2 blockchain. And I think we're going to have an occasion to talk a little bit more about this.
Nice to meet you folks. I'm Sylve. I'm the second most French name on this panel. I'm the co-founder and CEO of Hyle. We're a lean blockchain specialized for provable applications. Think of it as right now we're trying to cram ZK and provability back into blockchains. What we're doing is designing a blockchain from scratch around the constraints of provable applications. The idea is that down the line, it won't be rollups. We'll just call them apps. And just in order to make this, I see you nodding along. I think we quite agree on a lot of things. Yes. And we just try to design and expand the design space for decentralized computing by building the best blockchain for you to do that.
People, three very different areas of ZK. So over the past several years, we've seen an order of magnitude or more efficiency in the innovation of proving systems, marked by proof generation time as well as proof size. Some examples of areas that have had impact include the use of smaller fields in Stark backends, fast composition of proofs, and for folding-based recursion or small fields, and the use of hardware acceleration. So which factors would you guys credit as having had the most impact on proving efficiency? And where do you think we'll get the next order of magnitude improvement from?
Okay.
Yeah, you can start, Jens.
Okay, yeah. So I think one thing that has got me increasingly excited are subject proofs and GKR. And the reason is that they to some extent, take commitments out of the equation, right? Like proving things, you can prove that to a certain depth without actually touching the commitment. So it reduces the commitment overhead and cost in a proof. So that's something that's got me excited. And people are working on that. And I think we're seeing a lot of different approaches. And I think people are collecting it and seeing that go to some sort of trick singularity where we finally get the proof system that has all the tricks. We're not there yet. So I think the next factor 10 is just getting from combining all those tricks. And then looking a little ahead, right? So Elon Musk has this notion of the idiot index, and the idiot index is if you're producing some sort of component, it has some cost to produce it, and the raw materials has some cost. And the idiot index is basically the ratio of those two, right? And if you think about proof systems, and we do have the notion of idiot index as proof systems, and Wei Dai gave a very nice talk where he was defining this notion of kappa, which was the cost of creating a proof, or say some cycles of a CPU or something like divided by the number of cycles that you're actually proving, right? So the cost overhead that it has to prove something and that you computed it rather than just computing it, right? And right now that's astronomical, right? I'm talking about close to a factor million or something like that, right? So it's insanely high, right? So it seems like there's a lot left on the table, right? And if we talk about a factor 10 or a factor 100, we're not even close to closing that gap, right? And I don't see any theoretical barrier. Well, we shouldn't get much, much further down, right? But that's some sort of new breakthrough or some new ideas. And I don't know, your guess is as good as mine as where is that coming from? That's why we do research.
I wouldn't necessarily say my guess is sure. I do think that's a very good point.
Yeah, so that I could rattle off and sit for an hour on the things that excite me. One of the things that is fascinating to me is that even the areas of the field of ZK that we thought were closed, everybody knows about Binius and binary fields and how they're going to change everything. And everybody really thought, let's say a year ago, that stocks worked on. They were settled into the Prime protocol, Deep Prime was set up, and then you really had to move to something like Binius to get the next step in performance. And then Jacob Fancy arrived. And he arrived with Steer, he arrived with Weir, he arrived with a quotienting method of Steer that was immediately reused by two different researchers to do folding without homomorphism, creating a slow seismic shift in the way that we're going to do stocks next year. We're at the stage where the innovations are arriving so fast still that even areas that were thought to no longer be virtuous fields of research actually wake up again through the arrival of basically the genius of one PhD student. So I'm really excited about the field that is going to continue to advance really, really fast. Where this is a kind of bad news is if you want to productionize an enterprise solution that will deliver proofs in one particular system, you're going to have to learn how to get a light footprint because the cryptographic proving systems are going to change under you so fast that if you overinvest into something that is not modular enough, that you cannot replace, then you're at risk of having to do a huge engineering lift in 1 year when your product becomes completely obsolete from a proving standpoint.
That's a phenomenal point. I think people often overlook the contribution of engineering and the modularity of engineering of a proving backend to the efficiency of the systems built on top of it.
Yeah. The nice thing about this is that we're understanding this a lot more. So the arithmetization side of this story has become a lot more mature. It is something that we now understand how to port from one stage to the next. In many ways, the CPU ASAs that we've seen that are centralizing around RISC-V are making provers commodities. I have my problems with those CPU ASAs, which I think are both insecure and inefficient. But I will recognize that they help companies figure out that commoditization and cryptographic replacement problem.
What interests me there are, so as the only non-PhD person on this panel, I'm trying to bring another view on this topic is, what interests me are also the ecological conditions that make it so that we're having this Cambrian explosion of research and new things and, how it comes up that one PhD student is able to revolutionize everything. But starts have been around for a bit now, to the point that some of us on this panel have proof systems named after them. And what I like to think about it is, I think it's a bit like the history of the steam engine. Like the first time we used the steam engine was not in steamboats, was not for the textile industry. It was the first use at the end of the 19th century was to pump water out of coal mines, because these engines were so badly inefficient and janky that the only place they could be used was just right next to the energy source. And by doing this, the engines got better and we applied them to different things. And I like to think of blockchains currently as like first for privacy with Zcash, then to just speed up rollups as the coal mines for ZK proving systems. And I think that's where like the ecological conditions reunite to create this Cambrian explosion. What interests me is also what's coming next. And I don't have a clear idea there. I have like ideas about like provable applications, trust infrastructure that rely on ZK, and that will be a textile industry.
I think that's a fantastic point. To touch on something that I think is a point of similarity between both Nexus and Lurk. As some of the teams in the industry, Polygon, ZK Sync, Velita, Succinct, RISC-0, have moved towards Stark backends, both of your teams have used folding backends and continue to use folding-based backends. I'd love to know a little bit more about why you chose to make that bet and how you see the optionality for using different proving backends evolving.
I'm going to start with the easy answer, which is we're not using a folding backend anymore.
My info's out of date.
No, I mean, this is a real topic, right? We were using a Nova-based proof system. Nova is based on Snark, on RISC-V, and therefore on Weta machine. Nova is based on Snark and therefore on elliptic curves. And we found that the cost of how we were engineering those particular commitments was too big, and that the engineering maturity of the field wasn't very compatible with our delivery deadlines. We had customers that wanted a particular project delivered on time and under budget. And so we switched to a small field backend, and our performance went from 55 times behind the competition to 3 times ahead. Now, of course, we did a couple of other things in the backend behind switching to small fields. That's not just abandoning Nova, but it means that we basically selected engineering maturity over the fantastic ZK IDs and rethought exactly how we were engineering the Lurk micro VM, so that when we had to crane lift it once again over a new cryptographic system, it would take us less time. It took us about 3 months to get a prototype, 5 months to get the perfect benchmarks and the exact performance we delivered for our customers. They're happy. And then we were really sad about folding. We had given up folding, which is one of those very nice ways of getting very cheap incremental proofs. And then Giacomo Fenzi arrived and explained to us how to do it on small field stacks. So we had ideas at the time. The work of Benedict Boons on limited bonded accumulation was already not published, but nascent. And we had got news that he had that one PhD student that was going to figure it out. The story turned out to be a little bit different, but we're very hopeful about how we're going to implement this next. Folding, that I'm sure I'm going to leave Jens to give us more detail about. Fantastic way to get extremely cheap incremental proofs, which is really useful because most of the proving use cases are not a one-off. They're a series. If you think about Lagrange, ZK Lagrange, ZK games, they're turns in the same game over and over again. And that technology gets us very efficient proofs for that.
Yeah, so Nexus was actually already implementing folding proofs before I joined. So I came into it, and I think the motivation was that one is that you get like low memory footprint, right? And you have parallelization you can get from folding. So it's like really lends itself to a proven network because you pass along the computation that different nodes would have to do in a PCD system to compute the proofs. And Nexus then, and there was an existing implementation from Microsoft of research that Nexus could look at. And Nexus then did like a ground up implementation of first Nova and then Supernova and Hypernova. And that's what we've been running in our network. We have been looking into Starks as well. So we have been looking at Stu in particular, exactly because of the benefits of small fields, right? And again, we had this tension like, folding is a really beautiful idea, right? So exactly as Francois said, we were keen on that, but then it also seemed that performance that by using other techniques. So we're like also very excited by the development that it seems like folding and small fields are now coming together again, right? And again, this is this proof convergence I was talking about, right? I think once you have different tricks in different, then people think hard about how can they get the best of both worlds, right? So I think we'll see a lot of tricks that pop up in one area and then get merged back in.
That's fascinating. I think there's a natural trade-off space between research-focused approaches where you're pushing the state of the art and the theoretical construction, and then the engineering approach that the industry is ossified towards across a number of teams.
And just one point of detail, because I know that Jens and I are obsessed about folding, but I name drop Giacomo Fenzi, and I realized that I need to give credit where credit is due. So Giacomo Fenzi did not publish about folding, he published about steer. Steer contains a quotienting technique that inspired two other groups of researchers that explain how folding works for Stark. So those group of researchers are William Wang, supervised by Benedict Boons at NYU, and Alan Chepiniak working on the Triton VM. And they're the ones that have recently published on folding on small field Stark.
Fascinating. And so just to make sure you're not left out, so can you talk to us a little bit about the choice of proof system that you've selected in Hyle?
One thing that we've realized when we were looking at how proofs were used in blockchain is that probably the biggest contribution to ZK2 blockchain is probably what is limiting them right now, is that everything has to fall back onto the upper limit of 300 or 250K gas to verify a Groth 16 proof. And that means that we have extremely fancy proving systems that use Starks, recursion, etc. And then you have to eat up massive amounts of latencies in order to cram all of this into a very tiny proof that you send on chain.
Preach.
I figured we'd be pretty aligned on that point. On our end, what we figured is maybe you actually want to use a specific proving backend for something, for instance, Noir, because it's really good for privacy and client-side proving. And maybe you want to use a multi-purpose ZKVM like Nexus, for example, for other things, which is actually what one of our builders has done. They've used Circom for ZK email, and then they've also used RIS0 for the proving backend for their ZK game. And we decided to just be the Switzerland of proving systems. All proving systems are equally beautiful. We want to support all of them. So we just very much decided not to make a trade-off on this.
Fascinating. I think that's a very good approach when you're building a hopefully general purpose platform. One of the areas I wanted to talk about, a little bit about hardware acceleration. We've seen a lot of teams over the last year announce partnerships with GPU providers, ASICs, and chip manufacturers. And that includes some of the largest teams in the space, as well as some of the up-and-comers. I'd love to know a little bit more about how each of your companies are thinking about hardware acceleration in the lens of, will your business use it, and what efficiency improvements you expect, right?
So Lock as a micro VM lives on top of an existing backend, and funnily enough, on top of an existing backend that kind of is constructed with a little bit more than a strict cryptographic forward. So at the moment, for example, our latest implementation, Lock 05, lives on top of Sphinx, which is a fork of SP1. So we're really inheriting the hardware cryptographic acceleration that lives on top of that existing system. Now, I know that there's a bunch of approaches to accelerate both some of the stack operations and that finishing wrapping Groth 16 proof that exists both in open source and in closed source on top of SP1. We're at the moment, the king of the land is still very much the GPU, but since this is a project based on the Planck 3 ecosystem, we're very excited about the work of Fabric that should give us production-ready performance. This is not something that we only improve on, but we're really careful about the power of that acceleration and making sure that we preserve our ability to inherit it as our proving system migrates from a cryptographic backend to another.
I guess I feel with the hardware accelerated companies, I think it's a difficult space to be because you have to predict the future into pretty far ahead. And I think that's very difficult to do in this space, right? Because research is changing the underlying algorithms quite rapidly, right? So it's so hard to find those fixed points that, you think are stable enough that you want to invest in actually producing an ASIC, say. We've looked into, and so we've not really pursued hardware acceleration so far. We focused on other things. We have looked at GPU acceleration because that seems like the lowest barrier to entry, but we've not quite made the bet of hardware for the future.
On our end, if I come back to the little story I was talking about before about the Steam engine, I think it's going to very much depend on, I'm going to use the same idea of ecological conditions for the proof system that you're using. For instance, on our case, we want to use every single trick in the book. On Hyle, we're going to aggregate a lot of demand for the proving services, basically. We're going to have a lot of applications that are posting provable blobs that eventually need to be proved and settled on Hyle. So over there, these particular things are going to be probably built on public input. So you massively benefit, the proving services that want to sell on Hyle massively benefit from hardware acceleration and ASICs because it's basically like mining. But on the other side, let's say you want more of a privacy preserving application, which is a completely different ecological condition. You're going to need, you cannot rely on the fact that everyone is going to have an ASIC on their smartphone. So you're going to need to use a specific proof system that is really amenable to the, again, ecological conditions of the thing that you're trying to prove in the particular condition that you're trying to use. So on our end, it's going to be a lot of that we need and a lot of back and forth that we need to have between us and the app developers to really steer them into. I think if you really want to use Noir on a client side type of thing, maybe you want to use more of this thing. Maybe if you rather have a very large computation over maybe you want to prove the edition of an image, like ZK proof that an image got edited and signed. These are operations that can be folded, for example, because they're really repetitive. So maybe you're going to use another type of resistor, and maybe you want to benefit from other acceleration. So I think it's a really interesting field to explore there.
I love that. 3 different companies, 3 different approaches. And as a final question, I'd love to touch a little bit on something specific to each of your projects. Francois, you build a decentralized ZK L2, and Sylve, you build a ZK L1. And both the architectures are quite dissimilar and quite dissimilar from anything else that we're seeing in the space. I'd love to know a little bit more about how each of you use ZK in the broader architecture of your chains and how you think it provides an efficiency improvement that's impossible without it.
So this is about the verification side of the house, right? So we were thinking about verification by the force of having to verify proofs, right? We've been developing ZK-like clients, and then we had to figure out what the problems exist, what the problems are when deploying them to blockchains. There's a crap ton of those. One of the things that caught us is that around 2020, there was a moment where blockchains tried to be scalable and figured out that you could have a single set of validators that operated on sharded state. And the advantage for that was really that you could process transactions in parallel. A couple of laboratories at a PFL, THZ, and Meta figured out in parallel and then built blockchains that could scale linearly through scaling the validator. Great. All of this is a thing that lives on today in what's called the fast lane of the Sweep blockchain, but really isn't a thing that caught on because we didn't need our token transfers to be faster. However, what we do need to have to be faster and parallelized is our proof verification. What does that mean? That means that the moment you're doing proof verification these days, even with ZK coprocessor, very often with other blockchains that try to speed up that verification, the model is trains leaving the station on a schedule. You're on a batch model. There's on a batch, you fill in the train until it's full. When the train is full, it leaves the station. If you want your transaction to be verified immediately, you're going to have to eat up a little bit of latency because, sorry, there's just not enough people on that train at the moment. It's not worth landing down on Ethereum and paying the 300,000 gas that is associated to it. So what we're building is something that, in our own terms, front runs the aggregate. You give us a proof, we exchange that for a certificate. The certificate contains a 2f+1 supermajority by stake, meaning a BFT-resistant certificate that tells you, yeah, your proof is completely valid. You can take that wherever you want on any blockchain you want without precompiles, without modification of those blockchains. Why? Because we spent the last 10 years developing blockchains so that they can verify multi-signatures already as it is. This is adversarially interoperable with a minimum amount of changes to any blockchain. For some blockchains, I need to send a little bit of information on a periodic basis to make you able to verify those multi-signatures. What that concretely means is you can get a certificate out of my decentralized network of validators, take it wherever you want, settle using the verification of your proof. You're done, right? Except you're going to count my validators and say, wait, you have 15 validators, that's not enough, or 20, or 120, and that's still not enough. I don't trust your stuff because I really want to settle on my validators on Ethereum, and I think those Ethereum committees are really the only thing, and that should be the law of the land. Okay, cool. I'll make that a ZKL2, exactly like everybody else does. There's nothing wrong with the aggregation model. Aggregation is great, but for security, not as a programming model. Meaning, we're going to aggregate those proofs, land the aggregate on Ethereum, develop that with EigenLayer so that we get shared restaking security. We're going to get all of those guarantees. What that guarantees is that if a validator misbehave and says anything wrong on a certificate, they know that 30 minutes later, they're going to get slashed because of the aggregate is going to get caught by Ethereum, even in a dishonest majority. That's why the ZKL2, you get dishonest majority guarantees. But you can still front-run the aggregate with something that is a meaningful level of security. And in fact, with the ZKL2 model, the best model we have for giving you the most amount of security out of anything that comes from an L2. And you get that without having to wait for the train leaving the station. It's having your own little bullet train. 1 mina for every one of you. Sorry, I feel a little bit passionate about this.
No, I love it. I think verification of zero-knowledge proofs is a incredibly important area, and it's one of the main points of value capturing in the proof value chain.
On our end, I think we do 3 things quite differently. If you look at, for example, what you would think of it when you say ZKL1, you would think of a Mina, something like Aleo. So the first thing that we would do very differently from like Mina is that there is no vendor lock-in. Like we don't require you to use O1JS. We very much think that all programming, like all ZK-DSL, ZK-VMs are beautiful, and you should use the right tool for the job. Maybe O1JS is great for one thing, maybe it's not that great for something else. So we just want you to have the flexibility to choose any language that you want. The second is, and I really agree with Francois' point, that recursion or aggregation is really good, but it may not be the one thing that you always want. It's great for security, but it's not great for just composition. If you are on Ethereum, composable smart contract calls are really powerful, but currently, if you want to do this as 2 ZK apps on Ethereum, it's definitely not possible or not with the same affordance. So what we do is what we call just proof composition. You just send both proofs at the same time with both inputs linked to each other and just verify, click, you're good. So that means that you can just use different proving backends with the same application and just make sure that everything is verified at the same point. So it gives you the same affordance of a sort of a world computer, but with ZK. And the third is we separate sequencing from settlement. So you just send your provable transactions. It's getting a reservation at a restaurant. You just say, okay, I'm going to come in 2 hours. You log that space, and then you can come in and say, okay, here's the proof. Move the state of my application from A to B. If you don't do this, it just means that you're going to end up with massive conflicts. So I think we're just trying to, remove the ZK out of the ZK apps type of things. We just want people to build applications without even thinking about what's underneath. We just want them to use the great affordances that ZK gives, which is privacy scaling and flexibility without having to think about the hassle.
Wonderful. And we're over on time, but I want to make sure I give Jens, you a chance to obviously talk about some of the great work you guys are doing. As a final question, and obviously we need a little bit of brevity on the answer on this one, but one of the things you've talked about externally is this idea that the computation within the Nexus network is additive, where everyone contributes to this kind of shared global computation with ZK, which is dissimilar from a lot of the other proving architectures for decentralized proving that we've seen other ZK VM teams talk about. If you can provide some context or a little bit of some information of what you guys are doing so differently that kind of results in this different outcome.
Not sure I want to claim that we're doing things completely differently and so forth.
Yeah.
People are aware that parallelization is a good thing, and other teams are doing that as well, right? I think one thing that works particularly well with folding is that it's actually fairly easy to do, right? So the folding schemes were designed with incrementally verifiable computation in mind. But it does turn out, and we figured out that you can do a proof carrying data kind of structure where it's more like a tree of computation, right? And that's what we have in our network, right? And that really plays very nicely in parceling out who does which piece of computation. So that's where we're getting that parallelization from.
Makes sense. Thank you, everybody, for coming, and thank you to the panelists. A round of applause, please, for everyone. Thank you, everyone.